differentiate an exponential, and what we saw is that if we have an exponential, so base e I'm talking about here, so the natural base, to some function, then we differentiate the power, that comes to the front, but the power does not change. So it's different to polynomials. Right? We don't change the power. Polynomials, of course, you subtract one from the power and you do it that way. Okay, but what happens if the base is not e? Pretty much done exactly the same. So if it's any other base, let's just call it a, the difference being that we will multiply it also by the natural log of a. Now I've used the notation log. A lot of people prefer to use ln because then it's obvious it's the natural log. But remember, if you see the word log and there's no base written there, we assume they are talking about the natural log. Okay? So why is this formula the same? Well, because the natural log of e, if you're talking base e, is 1. So it doesn't appear in the other one. So yeah, technically you are multiplying by the natural log of the base. So yes, something like this. The world's easiest calculus question. Y equals e to the power of x. You want to differentiate it. Differentiate x, you get 1. It's e to the x. Differentiate e to the x, you get e to the x, which is interesting in itself. The exponential curve, what it's basically saying is the slope is always equivalent to the y value, hence why the exponential goes and gets steep real quick. E to the 5x then would simply be 5e to the 5x. Any linear function really, it's just the coefficient of x. So 4e to the 4x. Doesn't have to be a linear function, we've got a quadratic there. So 2x plus 3, e to the x squared plus 3x plus 2. Product rule. Write down the first diff the second plus write down the second diff the first. Write down the first, 3x squared. Diff the second, it's now an exponential function that we're differentiating. So 4e to the 4x plus, write down the second, e to the 4x, diff the first, 6x. With these exponential questions, we're always going to get a common factor when you think about it, because the e to the 4x is always going to be in both terms here. So factorise that out. We've also got a common factor of 6x there. So 6x e to the 4x, 2x plus 1. Get into the habit of factorising your answer. Okay? So why bother? Well, because if you're then going to go and use it, say you want to find stationary points, well, you've got to equate that to be equal to 0, and you need it to be factorised. Because that's our rule, when an equation equals 0, one factor equals 0 or another factor equals 0. So it's a good habit to get into. Anarchy. Bring down the power, 7. Lower the power, 6. Diff the inside. There's a little bit of manipulation there to be done. There we go. 21 e to the 3x. E to the 3x plus 2 all to the power of 6. Quotient rule. Square the bottom. Write down the bottom. Diff the top. Oh, look at the top. World's easiest derivative. Minus, write down the top. Diff the bottom. Oh yes, world's easiest derivative. E to the power of x. But this is where we've got to be careful. It's so easy to make a silly mistake here and go e to the power of x times e to the power of x is e to the power of x squared, of course, is the silly mistake a lot of people make. Add the powers. So we have e to the 2x plus 3 to the x minus e to the 2x. Tie these up. Oh, actually cancels those e to the 2x's. We've got 3e to the x over e to the x plus 3 all squared. Why do we do calculus? Well, one of the first sort of questions we had was finding equations of tangents. So we're going to do that. Notice the y value, I've got the exact value, I haven't approximated, of e squared plus 1. I mean, it is a number, we just don't know what it is, of course, because we'd have to work out e, and e's irrational, and we don't know what that. So alright, differentiate, we get 2e to the 2x. That, of course, is not the slope, but it is the formula that allows us to find the slope. We're subbing in the x value of 1. Our slope is 2e squared. Point slope formula. Now, again, people can make mistakes here because it's a bit weird having a slope of 2e squared. Again, it's just a number. It's just the coefficient of x. That's what you write it down as. So it's no different than normal numbers. We collect like terms, like we do in algebra as well. And it's unusual looking, but that is a straight line. Even though e looks like it's another pronumeral, remember, no, it's representing an irrational number. It's a number. So we have a linear function there. We've got x to the power of 1 there. We've got y to the power of 1. That's a linear function. So 2e squared x minus y minus e squared plus 1 equals 0 would be the equation of that tangent. Base is not e. Not a problem. We differentiate it as normal, but we also multiply by the natural log of the base. So 2x log 4, 4 to the power of x squared. Notice I've put the log 4 in parentheses there. I think that's really important, otherwise you're going to get mass confusion, because if I didn't have those parentheses, it would look like I'm saying the log of 44 to the power of x squared. If I put the log 4 first without parentheses, it would look like I'm saying the log of 42x. Right, and if I put it at the end, it just looks weird, because I'd have 2x4 to the x, that looks strange. So I just whack some parentheses around it. It's very clear what the things are. Oh, hang on, we haven't done this yet. Y equals the log of x, but we now can do it, because all I've got to do is rearrange my equation. I'll make x the subject, because logs are the inverse function of exponentials. So that's the same as saying x equals e to the power of y. So instead of differentiating y with respect to x, I can differentiate x with respect to y. Well, it's easiest derivative, it's e to the power of y. But I'm not interested in dx to y, I'm interested in dy dx. Just turn the whole thing upside down. There's my answer. It's in terms of y instead of in terms of x, but it still works. So if I was to substitute the y value in for the point, I would get the slope. Now we don't often do that because we're dealing with functions. And that's why we tend to have them in terms of x, because with a function, for every x value, there's a maximum of one y value. But the reverse is not true. For every y value, there might be multiple x values if you think of a curve. So whilst I will substitute the y value in, which point are we referring to? And so often we will convert back, and I can do that because I know what e to the y is. E to the y is in fact x. So I know the answer is 1 on x, so I sub the x value in. Say, do you really have to? No. Working with the y value is perfectly fine. It's unusual to do it that way, but it works. I mean, you're going to get the right answer. Okay, let's start off with just a couple of questions.